Hello there. So this is video number 1 of section 4.2. In the first section, we introduced vector spaces, and we looked at some really interesting sets which could be vector spaces, and then looked at some really interesting sets which could be subspaces of vector spaces. And so we ventured a little out of Rn. We looked at like polynomials and matrices as vector spaces. But this section I actually want to return to Rn or Rm and look at a few specific subspaces which arise when we look at matrices. And so I claim that we've actually already seen the two subspaces we're going to focus on this section. We just haven't called them subspaces quite yet. Before we jump into that, though, I want to start off with sort of a motivating example. This is a problem we did way back in section, I want to say it was 1.5, when we introduced homogeneous equations. So remember, we had a way of describing all solutions to a homogeneous equation defined by a matrix. Specifically, this was representing all solutions in what we called parametric vector form. And so this problem is actually a problem just out of that section. So I would highly recommend pausing the video, working through it, and then I will work through it on the board. All right, so it's funny, that would be a really weird thing, without the pause. All right, so, and what's really funny about it too is I pause myself to account for the pause. Anyways, working through this. So we want to describe all solutions to the homogeneous equation. That means first we have to put A into RREF form. Thankfully, the example I chose, and this was actually purely coincidence, I just sort of picked a matrix that looked relatively good, only has one step to put it in RREF form. So notice here, I've got the 1, 0 I want in the first column. I've got a 1 in the second column, but I just have to clear out that 3, and then we'll actually be done. Well, not done with the problem, but we'll have put it in RREF form. All right. So remember that this corresponds to the two equations . And since we're working with homogeneous equations, of course, we don't need the right-hand side of this, the augmented matrix, right? We can just work with the coefficient matrix because we know that the coefficient matrix because we know that the right-hand side of these equations will always remain 0. And so what we can do now, so remember putting this in parametric vector form, we want to solve for the two variables here, x1 and x2, which are not free. So I can just solve each of these equations. The first one for x1, and the second one for x2. So if I want to put this in parametric vector form, remember what I want to do now is sort of just assign these parameters, I guess hence the name parametric vector form, for x3 and x4. And remember what that means is I'm just going to let x3 equal some real number s and x4 equal some real number t, where here s and t, again, s and t are both contained in the set of real numbers. So once I've done this, this means that every solution, which is a vector of length 4, must look like the sum of the following two vectors. So first vector we allow to correspond to our x3 parameter, and the second vector we let correspond to our x4 parameter. And so this would be how we could describe all solutions to this homogeneous equation. So specifically note, what this is telling us is that all of these solutions are linear combinations of the following two vectors of length 4. And so, if we just assigned some real number, so for example, if s equals t was equal to 1, then I could add these two vectors together and get some definite vector that was in the null space of, or sorry, I'm using words before I've defined them, that was a solution to the homogeneous equation ax equals 0. So I've already sort of said the next definition on accident. The set of all vectors which are a solution to this equation has a name, which is the null space. And so that is the specific set, or what we'll see soon, subspace that I want to talk about in this lecture. But keep this in mind, because we will come back to this solution later in the video. So we've seen how we can find a vector that is a solution to the equation ax equals 0, right? I just erased that example. So yeah, like I said, keep that in mind. All right, so definition. We say that the null space of an M by N matrix A is the set of all vectors in Rm Rn that satisfy ax equals 0. And so the set notation for this, we would say that NUL of A is equal to the set of all x in Rn such that A times x is equal to 0. So, a few things with this definition. Notice that these vectors are in Rn, and notice that we will often abbreviate the null space with NULA. So remember, if A is an M by N matrix, that means it has N columns, and so specifically the null space is a subspace of Rn. That means each vector in the null space is a vector of length n. Because remember, we're talking about these vectors x, right? So in the matrix equation ax equals 0, the x vectors are always vectors of length n. So it turns out checking if a vector is in the null space isn't terribly hard, right? So if we let A be the same vector we checked before, or the same matrix, excuse me, that we had seen previously, then we can very quickly verify that a vector is in or isn't in the null space. So if I want to verify that this vector v is in the null space and that this vector u is not, all I need to do, well, the defining quality of being in the null space, right, is that you are a solution to the matrix equation ax equals 0. So all we need to do to check, well, is this vector in the null space, is check does a times v equal the 0 vector. Well, a times v, 1, 3, 5, 0, 0, 1, 4, negative 2, times 1, negative 2, 1, 1. And we do our matrix vector multiplication dance. And sure enough, I get that this is equal to 0, 0. And then lastly, A times U. Well, if I do my matrix vector multiplication dance, notice I would match up 1, 3, 5, 0 with 1, 2, 1, 3. And so that would get me the vector 1 plus 6 is 7 plus 5 is 12. And then 1, 4, negative 2. 2 plus 4 is, let's see, 2 plus 4 is 6 minus 6. Oh, that get me a 0 there. But notice that since this is not the 0 vector, U would not be in the null space of A. So checking this, sort of just the quick verification, is said vector in null space of A, is as simple as just checking the product A times vector. And so certainly, so we can check V is in the null space and U is not in the null space. But what I want to convince you of, like I had said, is that the subspace, or is that the null space is actually a subspace of Rn. So using the techniques we had introduced in the previous section, you should be able to work through this and prove this. So again, I'd highly actually recommend pausing the video here and before I prove it on the board, proving the theorem I'm about to put on the board. Because really this proof just amounts to checking the 3 things that we need to check to verify that something is a subspace. So we'll say let A be an M by N matrix. Then the null space of A, MUL of A, is a subspace of Rn. Your book sort of states this theorem another way, which I'll put on the board, but I'm a little confused as to why they even bothered stating it this way. Equivalently, the set of all solutions to a system AX equals 0 of homogeneous equations is a subspace of Rn. And again, that sentence is saying the exact same thing, and so I'm not sure why your book decided to say the same thing twice, but I'll sort of stay consistent with the book here. So what you want to show, again, is that the null space of A is a subspace of Rn. So remember, this means you have to work through 3 things. You have to show that it's closed under addition. You have to show that the 0 vector is in the null space. And you have to show that it's closed under scalar multiplication. So pause the video here, try to prove it on your own, and then I will prove it on the board. All right. So we want to show first that this is closed under addition, right? So what we want to show is that if V1 and V2 are in the null space, then V1 plus V2 is in the null space. And to do this, we just use our matrix vector addition properties. So remember, if V1 and V2 are in the null space, this means that, well, A times V1 and A times V2 are both equal to the 0 vector. So what we want to show is that, well, A times V1 plus v2 is equal to the 0 vector. But remember, I can distribute A through this sum. So this is equal to AV1 plus AV2. And at this point, notice each of these terms is equal to 0. And so, of course, 0 plus 0 is just equal to 0. And so, if v1 and v2 are in the null space of A, then v1 plus v2 is also in the null space of A, and we have closure under addition. So the second property we want to show is that 0 is contained in the null space of A. This one might be the most straightforward property to show, because to see that the 0 vector is contained in the null space of A, all we have to do is verify the always true fact that anything times the 0 vector is equal to the 0 vector. So we've got that the 0 vector is always contained in the null space. Finally, we want to show that the null space is closed under scalar multiplication. So we want to say if v1 is in the null space of A, and C is any real valued scalar. So we'll just say in C is a scalar. Then C times v1 is in the null space of A. So this would be closed under scalar multiplication. Well, and this again is actually sort of just using our matrix vector properties. So if v1 is in the null space of A, of course that means A times v1 is equal to 0. So we just want to verify that, right, that this product, A times quantity C times v1 is equal to 0. But remember, the big thing we get to do with scalars is just factor them all the way out of this equation. And I love working with 0 in math because it's just so easy. Factor C out, A times v1 is equal to the 0 vector, and once you're multiplying by 0, everything just turns into 0. And so it's closed under scalar multiplication. So going through the traditional way, well, I guess the strict definition way of proving that the null space of A is a subspace of Rn, we've verified it. So this is probably the main topic of this video. The null space of any matrix A is a subspace of Rn, where, remember, the value n corresponds to the number of columns in A. All right, so I claim that we could have done this in an easier way, so that we actually didn't even need to go through this whole proof. I still wanted to because I think it's very good practice, checking all three of these things. But remember the example we looked at the beginning of this video, where I had said, we've got this way of describing all solutions to a homogeneous equation. So I want to go back to our example. So remember, we described all solutions to the homogeneous equation AX equals 0 in the following way. So remember, each solution vector x was the sum of the following two vectors. So why is this important? Well, so remember, we now know that the null space of this matrix is a subspace of Rn. We proved that in the sort of straightforward definition way. But notice by describing the null space in this way, I'm going to let this vector be v1 and this vector be v2. What I've actually done is in this example, I've shown that here the null space of A is equal to the span of v1 and v2, right? Because notice here, every vector that's in the null space has to be a linear combination of these two vectors, right? Every vector looks like this, where s and t are just any two real numbers I've chosen. So every linear combination of v1 and v2, this vector and this vector, is in the null space of A. So therefore, the null space of A is just the span of these two vectors. And so notice, this here actually is enough to just show that the null space of a matrix is a subspace of Rn. Because remember, the span of any set of vectors is always a subspace, as we showed in the first section. And so this method actually can be used to find what we call a spanning set for the null space of any matrix. So the method we just used, or the method we used at the beginning of this video, and so here, spanning set, we mean basically just a set of vectors whose span is equal to the null space of A. So we can actually find, again, for any matrix A, if we collect the vectors in the parametric vector form, and we basically just sort of calculate their span, well, that will always be exactly the null space of A. So that is, if we want to find a set of vectors whose span gives me the null space of A, I just find the solution to the homogeneous equation in parametric vector form, and that gives me a set whose span is the null space of A. And notice again, this fact right here immediately proves that the null space is a subspace because of what we showed last video. And so that's where we will end. A few quick notes on this method. Notice that in this example and in this method in general, because each vector sort of represents a different free variable, these vectors that produce a spanning set for the null space of A will actually always be linearly independent. And that's really important because of what we're going to introduce next section. And you can sort of see the reason being, notice that since each vector corresponds to its own free variable, if you look at the rows corresponding to the free variables, they're always going to sort of guarantee that these are linearly independent, right? I've got a 1, 0, 1 here, 0 here, 0 here, 1 here. And so that sort of alternating of 1s and 0s guarantees that these two vectors can't be dependent. On top of that, the number of vectors in this set, notice, was equal to the number of free variables I had in my homogeneous equation. That will always be true as well. So if I want to find a spanning set for the null space of A, this method will always produce a spanning set that contains a number of vectors equal to the number of free variables. So this is the null space of A. Next video, we will look at what is called the column space of A.